around the world have problems with the waste and harmful emission. The aviation industry is a significant contributor. Aircraft emissions are responsible for a large portion of global greenhouse gases, 900 billion to 1 trillion kilograms of CO2 equivalent annually. But there is a hope. Sustainable aviation fuel is a clean energy technology that converts waste and reduces the emission. There are four main pathways to produce SAF, each helping to convert waste into clean aviation. The first one, HEFA, hydroprocessed ester and fatty acid. The second one, ATJ, alcohol to jet. The third one, feature drop, FT. The last one is power to liquid.
Here at National Cheng University, we have taken a step further by combining HEFA and PTJ pathways. We produce a highly efficient and sustainable SAF. Our novel process can be divided into 6 zones. Let us go through them one by one. Zone 1, transesterification. Transesterification process cleaves the ester bonds in triglycerides, forming 3 moles of FAME at 50 to 60 degrees under mild pressure. Zone 2, FAME hydrodeoxygenation. FAME undergoes hydrodeoxygenation in the presence of hydrogen and a suitable catalyst to remove oxygen at temperatures of 3 to 400 degrees Celsius and 30 to 100 bars of pressure, yielding normal alkanes in the range of C15 to C18. Zone 3, PP pyrolysis. Polypropylene pyrolysis reaction takes place in a batch reactor at 420 degrees Celsius. The dominant pyrolysis product are branched paraffins and olefins. HP Zone 1. Glycerol steam reforming offers higher hydrogen selectivity per carbon atom and a lower net carbon footprint as the feedstock is biomass derived. HP Zone 2. Methanol steam reforming can contribute to low carbon or carbon neutral hydrogen production, making it a valuable hydrogen source. Zone 4. Final preparation. SAF fractions derived from hydroprocessed fog and pyrolysis polypropylene are individually preheated in a batch reactor system to target temperatures optimized for viscosity alignment and miscibility enhancement.
Simulation studies are reliable only if they use real-time data to build model. Our design is based on the pilot-scale SAF production unit in the Energy Engineering Lab at NCKU. Palm oil industrial grade was first filtered and stirred. The feedstock was heated, kept and mixed with methanol and acid catalyst at 70 degrees centigrade for 30 minutes. This mixture was stirred overnight. The oil-alcohol mixture was separated and the oil-rich layer, biodiesel, was stored at ambient temperatures. This biodiesel was then sent out to a fixed bed reactor loaded with catalyst, where under a hydrogen-rich environment and high temperature and pressure it formed sustainable aviation fuel. The polypropylene was processed in a stainless steel vacuum pyrolysis setup. 100 grams of PP was loaded, after which the reactor was sealed and subjected to vacuum pressure. The reactor was heated at an average of 5 to 20 degrees centigrade per minute to the final temperature of 500 degrees Celsius. Volatile hydrocarbons exiting the reactor was passed through 2 condensers. The first collected heavy condensate and the second collected light condensable products. These pyrolytic oils were analyzed using GCMS to confirm the composition.
This approach can reduce the complexity and cost associated with separate production and blending stage.
We are proposing a novel hybrid pathway to increase the yield of the SAF by combining HEFA and PTJ pathway. As shown in the table properties of the comparing our novel SAF with the traditional GA1 or GP5 which are available in the market, our product match and create even better result than other jet fuel.
The novel industrial design shows a CO2 emission of 12 kg per hour, almost 80% lower than the other conventional technologies. Targeted towards waste utilization, this is one of the first reports on diversifying SAF feedstock. In situ production of hydrogen broadens the economic perspective and reduces the reliance on external sources. Conventional processes already existing can use the hydrogen generation system on the sidelines, making it completely feasible. The excess hydrogen produced can be sold in the market to generate further revenue.
Together, we can reduce the waste and create brighter future.